Hello everyone, welcome to Chem Ki Chemistry. In this video, I am going to teach you about the electronic configuration of elements. This is again one of the very important topics of the chapter structure of atom. In the last video, I have told you that the ultimate location of the electrons is orbitals. Okay. So instead of filling the orbits, or we can say shells, which we were doing in the junior classes, in the latest electronic configuration, you will be filling the orbitals. Okay, I repeat, in the latest electronic configuration of elements, you will learn how to fill the orbitals in a correct manner. So before I start the electronic configuration, I would like to tell you three principles. Okay, because these principles will help you in doing the electronic configuration correctly. The very first principle is Pauli exclusion principle. This principle says that only two electrons can be present in one orbital. Okay, so you cannot fill more than two electrons in a particular orbital. Okay, for example, if you are talking about s orbital, so in s orbital, you know that you will fill only two electrons. Okay, similarly, if I talk about P, so in P subshell, you know that in P there are three orbitals, Px, Py and Pz. Okay, so there are three orbitals, so maximum 6 electrons can be filled. Okay, so don't get confused, beta, that in S we are filling 2, but in P we are filling 6. Why? Because P is a subshell, and in P subshell there are three orbitals. Okay, and one orbital can have two electrons, right? So three orbitals would have maximum 6 electrons. Similarly, if I talk about d subshell, so in the d subshell you have 5 orbitals. 5 orbitals means maximum 10 electrons. F subshell, you have 7 orbitals, so maximum 14 electrons you can fill. Okay, so you need to remember this thing about the Pauli exclusion principle. Okay, now come to the second point. In the second principle, that is the Aufbau principle. Aufbau principle. In Aufbau principle, you must know that we fill the orbitals in increasing order of their energy. Always remember. See, when you take admission in a school, you always start from nursery. Okay, you don't take admission in class 12th and then go to 11th and then move to 10th. You don't do like this. Okay, you always go in ascending order. Okay, that means from lower class to higher class. Similarly, Aufbau also said that while you fill the orbitals, you will always go in the ascending order. That means lower energy orbital would be filled first, and then you will move towards the higher energy orbital. Is that okay? Now, what is the formula to calculate the energy of the orbital? So, to calculate the energy of the orbital, the formula is N plus L. Always remember this. This is called Aufbau formula. N plus L. That means the sum of principal quantum number and the azimuthal quantum number. Okay. For example, if I ask you that you are having the 3D orbital and you have the 4s orbital. Okay, now which is to be filled first? So you calculate the energy of both the orbitals. In case of 3D orbitals, it is 3 plus the value of L for D, it is 2. So 3 plus 2, it gives you 5. Whereas in case of 4s orbital, the value of N plus L will be 4 plus 0. That gives you 4. That means 4s orbital energy is lower than that of 3D. It is lower. So you will fill the 4s orbital first and then you will fill the 3D. Okay, now you cannot calculate this N plus L value every time and then find out that which orbital is to be filled first and which is to be filled later. So there must be some particular order of orbitals which should be on your tips. Okay, so this order I tell you how to remember this order of orbitals so that you can quickly do the electronic configuration in that order. So how you can make the Aufbau chart so that you remember the sequence of the orbitals which are to be filled. The the easiest way is this. What you do, you first write the number from 1 to 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Then you start removing the numbers from the top and the bottom. Okay. One number you will eliminate from the top, and the another number, the last number, you will eliminate from the bottom. Okay. So when I eliminate 1 and 8, in the next row, I will be writing these numbers. Okay. Then again I will eliminate the first number and the last number. So I will write like this. Again I will eliminate. So I will be having this type of pattern. Okay. Now in this pattern, what you do, in the first row, you just put S. Okay. All the numbers, you put S with all the numbers. In the second row, you put P with all the numbers. In the third row, you put D with all the numbers. In the last row, you put F with all the numbers. Okay. Then you start making the arrows like this. Okay. So you can draw the arrow in this way. So when you go according to these arrows, you will get the direction of the filling of orbitals. Okay. So if I start deciding that which orbital is to be filled first, so you can see that my arrow is starting with 1s. So I will write 1s first. After 1s, I will fill 2s, then 2p. Then after 2p, the arrow is going towards 3s. I will fill 3s. Then I will fill 3p. After 3p, this is something important to note, that after 3p, I am not moving to 3d. Rather, I am moving to 4s. Okay. And after 4s, I will be filling the 3D. Okay. So if you are not knowing this sequence, not aware of this Aufbau chart, then you may miss this kind of mistake. Okay. So always remember to follow the Aufbau chart. Okay. After 3D, you will be filling 4P. After 4P, you will fill 5S. Then from 5S, you can see that you are going towards 4D. Then next is 4D. After 4D, you have 5P. Okay, so on. You can do the electronic configuration in this order of the orbitals. Okay, so always remember to stick to this Aufbau chart while you are filling the orbitals with the electrons. Okay. Now the next principle which we need to learn, that is the Hund's rule. Okay, so let's begin this principle as well. Hund's rule, this is very simple to understand. So this rule says that when you are filling the orbitals of the same subshell, for example, if I ask you about the beta S subshell, so in the S subshell there is only one orbital, one S orbital. Okay, one S orbital. So Hund's rule is not to be of any use in this case in S subshell, but in case of P subshell, that so you know that in P subshell we have three kind of orbitals. One is Px, another is Py, and the third one is Pz. So when you are filling the three orbitals of a same subshell, okay, then you need to follow the Hund's rule, and Hund's rule says that you need to fill them singly first. Singly means you will be sending one electron each, okay, in all these orbitals, and then you will be doing the pairing later on. Okay, for example, if these three orbitals are to be filled with the 4 electrons, okay, then which two methods which will click you? The first method which can click you is this, that you will fill the electrons, the 4 electrons like this. Okay, and the second method you will adopt, that will be like this, that you will fill the all the 3 electrons independently, and then the 4th electron you will do the pairing in the first orbital. Okay, so you can see the difference in these two cases. In the first case you are directly doing the pairing, but in the second case you are filling the orbitals singly first, and then you have done the pairing. So the second option is as per the Hund's rule. So this is the correct option, and the first method of doing the electronic configuration is the wrong option. Okay, so always remember that when we are filling the orbitals of a same subshell, then we must fill them singly first. Okay, we must fill them singly first, and then we can start the pairing. We will not do the pairing right from the starting. So here you need to take care. Now we will learn how to do the electronic configuration of a few elements. You can see that I've written some elements on the screen. So the first element is hydrogen. What we will do? We will do the electronic configuration as per the atomic number which is mentioned. You can see that in all the elements there is a number mentioned against each element. So these numbers are basically the atomic number. An atomic number is equal to the number of electrons. Okay, so whatever atomic number is written, the same number of electrons we have to fill into the orbitals. Okay, so let's begin. The first element is hydrogen. The number of electrons, it is 1. So you will use only the first orbital, which is 1s. And in 1s, 1 electron will enter. Okay. Now, the next element is lithium. In this case, you can see there are 3 electrons. As I have told you that the capacity of one orbital to hold the electrons, that is 2. That means out of the 3 electrons, the 2 electrons will go in the first orbital, which is 1s, and the remaining third electron will enter into the next orbital, which is 2s. Okay. Now, next is oxygen. Oxygen is 8. Number of electrons, they are 8 in number. So, how you will do? You will write 1s2, 2s2 and 2p4. Why 2p4 here? Because this thing also I have discussed with you that in the p subshell, there are 3 orbitals. Okay, px, py and pz. There are 3 orbitals. That means in the p subshell, there is a capacity of holding 6 electrons. Okay, so I can fill the p subshell up to 6. Okay. Now the next is neon. Neon atomic number is 10. That means 2 more electrons you need to add. Whatever configuration is of oxygen, you can retain the same configuration, or in case of neon, only the thing is that you need to add extra 2 electrons. So what I will do, I will write 1s2, 2s2, and in 2p, I will add 2 more electrons. That means the configuration becomes 2p6, right? Now the next is sodium. In case of sodium, you will write 1s2, 2s2, 2p6 because it counts 10 electrons. Now the next electron, the 11th electron, it will go into the next orbital. So you can see that after 2p, the next orbital is 3s. So the next electron will go in 3s. Okay. There is another alternate of doing the electronic configuration of sodium. That what you can do, see, when you increase the atomic number, you will see that the configuration starts getting lengthier. Okay, so if you want to write the configuration in a concise manner, so what you can do, you can take the help of the nearest noble gas. For example, in case of sodium, the nearest noble gas is neon. So you can just write neon, because neon includes the 10 electrons. Okay, so when I mention neon, that means that has included the 10 electrons, and the last electron, the 11th electron, will enter into the next orbital, that is 3s1. So this is another alternate of doing the electronic configuration. Okay. The next is scandium. In case of scandium, what you will do, you will write the configuration in this way: 1s2, 2s2, 2p6, 3s2, 3p6, okay, and then 4s2. Now you can see that this counts up to 20. When you total the electrons, then you will see that the total number of electrons till now is 20. So the next electron will go in the d orbital, 3d orbital. You can see here in the Aufbau chart that after 4s, what you are filling, after 4s, you are going towards 3d. Okay, so this is the configuration of scandium. The next important thing is to do the configuration of the ions, especially the cations. For example, if you are given such type of case, here I have taken two examples. One is the ferrous ion and another is the nickel ion. Okay, I'm taking the ferrous ion case first. If you are asked to write the electronic configuration of ferrous ion, this is something where the children make mistake. They often make mistake in these type of configurations. What the children do, the children remove the two electrons from the iron. That means they assume that iron is having the 26 electrons. That means 2 positive. So 2 positive, that gives you 24 electrons, and they do the configuration of Fe2 positive assuming the 24 electrons. Okay, and this is a wrong approach. Okay, now what is the right approach? The right approach is that first you do the configuration of iron. Iron, the nearest noble gas is argon. Okay, now up to argon 18 electrons have been filled. Now the remaining electrons, how many electrons are left? The remaining electrons are 8. Okay, the remaining electrons I will write like this: argon 4s2 and then 3d6. Okay, so first you have done the configuration of iron. Now you will do the configuration of Fe2 positive, which is ferrous ion. Now what you will do, instead of removing the 2 electrons from the 3D, because what you can do this configuration in two ways. One way is this, that you have removed the electrons from the 3D subshell. Another way is this, that you are removing the 2 electrons from the 4s subshell and then you are writing 3d4. Now out of these two, 3d6 you are writing here. Okay, now out of these two, which approach is the right one? So this is the right approach. Always remember, the first approach is a wrong approach. Why? Because in the first approach, you are removing the electrons from the 3D. Okay. But you are supposed to remove the electron from the 4s. Why? See, this is very simple to understand, that when we have to remove something, so what you do, you always take out something from the outer part of the substance. For example, if you are taking out your clothes from the almirah, so what you will do, you will first take out the clothes which are lying at the outer part of your almirah. Okay, instead of going inside. So same will happen here, that when you are removing the 2 electrons, then you will remove the 2 electrons from the 4th shell, because the 4th shell is lying at the outer side. Okay, so this is the right approach and the first approach is the wrong approach. I take one more example of this. Similarly, in this case, Ni2 positive, what you will do? First, you will do the configuration of nickel. Nickel is 28. So, the configuration of nickel would be like this: 4s2 and then 3d8. Now, for doing the configuration of Ni2 positive, you will remove the 2 electrons again from the 4s. Okay, from 4s orbital you will remove, not from the 3d. Okay, so this is something very important to remember. Okay. Now in the last, I am going to tell you about the exceptions of the electronic configurations. You can see that I have mentioned chromium and copper. So these two are the elements which show the exceptional electron configuration. There are few other elements as well, but these two are the important ones. Okay. So let's take the case of chromium first. In case of chromium, the atomic number is 24. Okay. So the nearest noble gas is argon. So I am writing argon here. Till argon, 18 electrons have been filled. Now the remaining 6 electrons you have to fill. So after argon, you will start with 4s, because the argon ends at 3p. Okay, so it will end at 3p. So after 3p, you have to start with 4s. So you are writing 4s2 and then 3d4. So this is the first thing which you will do if you are not aware that the chromium is showing the exceptional electronic configuration. Okay. So this is a wrong electronic configuration of chromium, because I have told that this is one exception. Now, one thing which is very, very important to know, not just for 11th class, for 12th class as well, in future also, that the half-filled and fully filled subshells are highly stable. Okay, half-filled and fully filled subshells are highly stable. Always remember this statement, because this is something which you will use in 12th class as well. There is a chapter, D and F block elements chapter, and lot of questions are based on this reason. Okay. So what I do, if I shift one electron from 4s to 3d, so what will happen? The 3d will acquire the half-filled configuration. The 4s will also become half-filled. Okay. I've told you what is the capacity of D. The capacity of D is 10. Okay, because there are 5 orbitals. So it can hold 10 electrons. But if I shift one electron from 4s to 3d, so the configuration will become like this. Argon 4s1 and 3d 5. So it gets the stability due to the half-filled configuration. So this is the right configuration of chromium. Same is the case of copper. Copper atomic number is 29. So if you are not aware, then you will do the configuration like this. Argon 4s2 and then 3d9. Again, this is a wrong configuration. Why? Because you know this thing, that fully filled subshell is highly stable. So if you shift one electron from 4s to 3d, so what will happen? In this case, the 4s will get the stability due to half filled, and 3d will get the stability due to the fully filled subshell configuration. So this is the right approach of doing the configuration for copper. Okay. So I hope that you have understood this video completely, and I request you all to practice the configuration of some extra elements, not restrict yourself to these examples which I have taken up in the video. So you can explore more elements and try the configuration of other elements too. Okay. If you have any doubt, then you can write it in the comment section. If you want any particular topic to understand, you want me to make video on that, then you can do that also. And if you like my video, then please subscribe. Okay. Thank you. Have a nice day.